In this lesson, we will delve into Task 2.2.2 of Project 2, which focuses on the design essentials of the collet chuck in the centering and clamping lace fixture. As a critical component of the centering and clamping lace fixture, the rationality of the collet chuck's design directly affects the fixture's performance and machining accuracy. We will explore in detail the working principle, design parameters, and the material selection of the collet chuck. Additionally, we will examine the elastic fault tolerance technology used in holding aerospace engine blades, a case that exemplifies the manufacturing philosophy of balancing rigidity and flexibility. This will aid in better understanding and mastering the design essentials of the collet chuck. In the machining process, the centering and the clamping lace fixture plays a crucial role, with the collet chuck being one of its core components. Next, we will discuss in detail the design essentials of the collet chuck. Working principle of the collet chuck. The collet chuck achieves centering and clamping of the workpiece through its elastic deformation. When subjected to axial force, the chuck undergoes radial contraction, tightly gripping the workpiece to achieve centering and clamping. This mode of operation endows the collet chuck with advantages such as high centering accuracy and uniform clamping force. For instance, in the machining of some precision parts, the collet chuck can accurately position the workpiece, ensuring machining precision and quality. Design parameters of the collet chuck. 1. Bore size. The bore size of the collet chuck is determined based on the outer diameter of the workpiece being machined. Generally, the bore of the chuck should be slightly smaller than the workpiece's outer diameter to ensure that the chuck can generate sufficient clamping force when tightened. Additionally, the tolerance of the bore size must be strictly controlled to ensure centering accuracy. For example, if the workpiece's outer diameter is D, the bore size of the chuck can be designed as D deltad, where deltad is an appropriate interference fit. The specific value of deltad needs to be determined based on factors such as the material of the workpiece and machining requirements. 2. Taper angle. The taper angle of the collet chuck is an important design parameter that directly affects the chuck's clamping and the release forces. A larger taper angle results in greater clamping force, but also requires more force to release. Conversely, a smaller taper angle results in less clamping force and requires less force to release. Typically, the taper angle of a collet chuck ranges from 110 to 120. In practical design, the appropriate taper angle should be selected based on specific machining requirements and the performance of the machine tool. For instance, in machining scenarios that require greater clamping force, a larger taper angle can be chosen. For situations where frequent loading and unloading of workpieces are needed, a smaller taper angle may be more suitable. 3. Length. The length of the collet chuck also affects its performance. Generally, the longer the chuck, the greater its capacity for elastic deformation, but the distribution of clamping force may become uneven. Conversely, a shorter chuck provides a more uniform distribution of clamping force, but its capacity for elastic deformation may be weaker. Therefore, when designing a collet chuck, it is necessary to reasonably determine its length based on the length of the workpiece and the machining requirements. Material selection for the collet chuck. The collet chuck requires good elasticity, strength, and wear resistance, so material selection must be particularly careful. Commonly used materials include spring steel and alloy steel. For example, 65 mm spring steel, with its high elastic limit and yield strength, is a commonly used material for collet chucks. When selecting materials, it is also important to consider the heat treatment process to ensure the chuck has excellent performance. Design steps for the collet chuck 1. Determine design requirements. First, based on the size, shape, material, and the machining requirements of the workpiece, determine the design requirements for the collet chuck, including bore size, taper angle, length, and clamping force. 2. Select materials. Choose appropriate materials according to the design requirements and determine the heat treatment process for the materials. 3. Conduct structural design based on the design requirements and the material characteristics. Carry out the structural design of the collet chuck, including its shape, slot type, and opening method. When designing the slot type, factors such as the depth, width, and spacing of the slots need to be considered to ensure the chuck's elastic deformation capability and clamping force. 4. Calculate clamping force. Calculate the clamping force of the chuck based on its structure and the material characteristics. The formula for calculating the clamping force is F equals K times delta times E times A. Here, F is the clamping force, K is the clamping coefficient, delta is the interference fit, E is the elastic modulus of the material, and A is the contact area between the chuck and the workpiece. 5. Perform strength verification after completing the structural design and the clamping force calculation. It is necessary to perform strength verification on the collet chuck to ensure it will not fail during operation. The strength verification includes checking the maximum stress and deformation of the chuck, elastic tolerance technology in aerospace engine blade clamping. Aerospace engine blades are high precision, high difficulty components, and their machining process demands very high standards for fixtures. In the clamping of aerospace engine blades, elastic tolerance technology is employed, embodying a manufacturing philosophy that balances rigidity and flexibility. Collet chucks are widely used in the clamping of aerospace engine blades. By reasonably designing the parameters and structure of the collet chuck, it is endowed with a certain capacity for elastic deformation, allowing it to compensate for manufacturing and installation errors of the blades to a certain extent, achieving elastic tolerance. For instance, when there are slight deviations in the blade dimensions, the collet chuck can adapt to these deviations through its own elastic deformation, ensuring the centering and the clamping accuracy of the blades. Additionally, the elastic deformation of the collet chuck can reduce damage to the blades, enhancing the machining quality. This elastic tolerance technology not only improves the machining precision and the quality of aerospace engine blades, but also reflects a manufacturing philosophy that balances rigidity and flexibility. In the manufacturing process, it is essential to ensure the rigidity of the fixture to provide sufficient clamping force, while also imparting a degree of flexibility to the fixture to accommodate workpiece errors and deformation. This philosophical approach offers significant insights for designing collet chucks and other fixtures. Practical application cases of collet chucks in the automotive manufacturing industry. Collet chucks are widely used in the machining of parts such as engine blocks and crankshafts. For example, in the boring process of engine blocks, collet chucks can accurately center and clamp the block, ensuring the precision and surface quality of the bore. In the electronics manufacturing industry, collet chucks are also used for machining some precision components, such as the packaging of mobile phone chips. In this lesson, we explored in detail the key design points of the collet chuck in the centering and the clamping lathe fixture design of Project 2. We first understood the working principle of the collet chuck, which utilizes elastic deformation to achieve centering and clamping of the workpiece. Next, we introduced the design parameters of the collet chuck, including bore size, taper angle, and the length. The reasonable selection of these parameters directly affects the performance of the chuck. We then explained the material selection and design steps for the collet chuck, which include determining design requirements, selecting materials, conducting structural design, calculating clamping force, and performing strength verification. Finally, through the case study of the elastic tolerance technology in aerospace engine blade clamping, we gained a profound understanding of the application of the manufacturing philosophy that balances rigidity and flexibility in the design of collet chucks. I hope that through this lesson, everyone will be able to grasp the key design points of collet chucks, laying a solid foundation for future work in machine tool fixture design.